Welcome to today's problem discussion. We'll be exploring problem number 1591, titled Strange Printer 2. This problem challenges us to think about grids and printing processes in a unique way. Get ready to dive into the details as we break down the approaches step by step. In this problem, we are working with a strange printer that can print a specific value on a rectangular section of a 2D grid. Initially, the grid is filled with zeros, and the printer allows us to select any subrectangle and assign a single value k to all cells within that subrectangle. The goal is to determine whether it is possible to use this printer to create a given target grid. The target grid is represented as a 2D integer array, where each cell holds a value between 1 and 60. To solve the problem, we need to return a Boolean value, true if it is possible to print the target grid, or false if it is not. This introduces an interesting challenge, as we must consider the constraints and sequence of printing operations required to achieve the desired result. To better understand how this works, let's look at an example. Suppose the target grid is a 3x3 matrix where the input is 111, 122, 111. In this case, the output is true because we can print the target grid in two steps. First, we print the entire grid with the value 1, covering all cells. Then, we print a smaller subrectangle that includes just the middle two cells of the second row with the value 2. By following this sequence, we achieve the target grid without overwriting any values incorrectly. This demonstrates that it is feasible to print the grid with this printer, and the solution is valid. Now consider another example where the target grid is 111, 333, 111. Here, the output is false. The reason is that the value 3, which appears in the second row, cannot be printed without overwriting the value 1 in the first and third rows. The strange printer does not allow us to selectively print values in a way that would preserve the surrounding ones, and thus it becomes impossible to achieve the target grid in this case. However, in a different example like 121, 212, 121, the output is true. One potential way to achieve this grid is to first print the entire grid with the value 1, then print the middle cell of the second row with the value 2, and finally print each diagonal cell with the value 2. This ensures all the values are printed correctly without overwriting anything unintentionally. Finally, let's review the constraints and edge cases. The dimensions of the grid are defined by m rows and n columns, where both m and n can range from 1 to 60. Each cell in the grid contains a value between 1 and 60. For edge cases, consider a single-cell grid, where printing is always possible since there's only one cell. For a uniform grid where all cells have the same value, the grid can be printed in a single operation. However, for grids with multiple overlapping layers of subrectangles, you need to carefully plan the printing sequence to avoid overwriting cells. Sparse grids, where many cells are zero, require similar attention to ensure that new values are printed correctly without disrupting existing ones. These constraints and edge cases highlight the complexity and strategic planning required to solve this problem. To begin, let's consider the brute force approach. The idea here is to iterate through all possible subrectangles in the grid and simulate the printing process. For every color K, we check if there exists a subrectangle that can be printed without violating the order in which the printer operates. The intuition is that each color should form a valid subrectangle, and the sequence of printing operations should preserve the grid structure. However, this approach faces significant challenges. The number of possible subrectangles grows combinatorially as the grid size increases, leading to inefficiency. Specifically, for a grid of size mxn, there are m squared, n squared, possible subrectangles, resulting in a computational complexity that makes this method impractical for larger grids. This inefficiency arises from the sheer volume of combinations that need to be considered. Now, let's explore a more structured approach, topological sorting via a directed graph. In this method, each color K is treated as a node, and we create a directed edge between two colors, say A and B, if color B must be printed before A. This dependency arises when B overlaps A in the grid. Once the graph is constructed, we check if it forms a directed acyclic graph, or DAG, using topological sorting. The intuition here is that the printer's constraints impose a dependency order between colors, which can be represented as a graph. If a valid topological ordering exists, it confirms that the grid can be printed in the required sequence. However, constructing the graph can be tricky due to the need to carefully handle overlapping regions. The overall complexity for this approach is O(m*n plus e, where e represents the number of edges in the graph. While this method is an improvement over brute force, graph construction and traversal can still introduce computational overhead. The chosen strategy for this problem is the optimized dependency resolution approach. Here, the key insight is to identify the minimum bounding rectangle, MBR, for each color K. The MBR is the smallest rectangle that can encompass all cells of a particular color. For the grid to be valid, all cells within this rectangle must either belong to the same color or to colors that are printed earlier in the sequence. By iterating through the grid, we validate each color's MBR to ensure that this condition is met. This approach stands out because it directly leverages the grid structure without requiring explicit graph construction. It is both efficient and intuitive, avoiding unnecessary computations. While it requires careful bookkeeping to track and validate the MBRs, it offers linear time complexity relative to the grid size, O(m*n), making it a practical solution. This strategy balances clarity and computational efficiency, which is why it was selected over the other approaches. In summary, the optimized dependency resolution approach is an effective method for solving this problem. It efficiently validates the grid's printing order by focusing on the minimum bounding rectangles of each color, ensuring that dependencies are respected. This approach strikes the right balance between computational efficiency and clarity, making it well-suited for the constraints of this problem. While some trade-offs exist, such as the need for careful validation of MBRs, the method's simplicity and linear time complexity make it a robust solution. In this problem, we need to determine whether it's possible to print a given grid using a sequence of subrectangle operations. Each subrectangle is filled with a single color, and the order in which these subrectangles are printed must adhere to specific constraints. The key challenge lies in ensuring that no higher priority color is overwritten by a lower priority one during the printing process. To begin addressing this, we consider a brute force approach. The intuition here is to simulate the printing process for each color in the grid. For a given color, we identify the smallest subrectangle that encompasses all its occurrences. Once we have this subrectangle, we validate whether it can be printed without interfering with the regions that belong to other colors that should come later in the sequence. This ensures that the constraints of the problem are respected throughout the process. To formalize our approach, we first represent the grid as an MXN matrix, where each cell contains an integer representing the color at that position. The colors are numbered from 1 to C, where C is the total number of unique colors in the grid. Next, we perform pre-processing to determine the boundaries of the smallest subrectangle for each color. Specifically, for each color K, we compute top_K, the smallest row index where the color appears, bottom_K, the largest row index where it appears, left_K, the smallest column index, and right_K, the largest column index. These boundaries define the minimum bounding rectangle for the color. By computing these boundaries upfront, we establish the regions we need to validate, making the subsequent steps more efficient. Once the bounding rectangles are defined, we validate each one to ensure it meets the problem's constraints. For a given color K, we check all cells within its rectangle, defined by top_K, bottom_K, X, left_K, right_K. These cells must either be the current color K or empty, meaning they can be overwritten. If any cell within this rectangle belongs to a different color K with a higher priority, the grid is deemed invalid. Additionally, we process colors in reverse order of priority, starting with the highest color C and working down to 1. This guarantees that when we validate a given color, all higher priority colors have already been printed and their regions are fixed. If all colors pass this validation step, the grid is valid, and we return true, otherwise, we return false. Several key insights help optimize our approach. First, focusing solely on the minimum bounding rectangle for each color significantly reduces the search space. Instead of checking the entire grid for every color, we limit our validation to the cells within these rectangles. Second, processing colors in reverse order ensures that higher priority regions are fixed before we validate lower priority regions, simplifying the validation logic. Finally, the pre-processing step, which computes the bounding rectangles for all colors, is efficient, requiring only a single scan of the grid. This efficiency, combined with the reduced validation space, makes the algorithm computationally manageable, even for larger grids. To implement this algorithm, we rely on a few key data structures. First, we use arrays to store the boundaries of each color. Specifically, top, bottom, left, and right arrays of size C store the respective boundary indices for each color. For example, top K holds the smallest row index where color K appears. Second, we use a Boolean grid to mark cells that have already been validated as part of a printed subrectangle, ensuring we don't revalidate them unnecessarily. Lastly, we use a set to track all unique colors in the grid during pre-processing. These data structures help organize the information we need to efficiently pre-process and validate the grid. Analyzing the complexity, we see that the algorithm is efficient. The pre-processing step, where we compute the boundaries for all colors, requires a single scan of the grid, which takes (m*n) time. For validation, we check each cell within the bounding rectangle of each color. Since the total number of validations is proportional to the number of cells in the grid, this step is also (m*n). Combining these, the overall time complexity of the algorithm is (m*n). In terms of space complexity, the boundary arrays require C space, where C is the number of unique colors. The Boolean grid requires (m*n) space. Therefore, the dominant term in space complexity is also (m*n). When applying this algorithm, it's important to consider edge cases that could arise. For instance, if the grid contains only one color, it is always valid since no overwriting can occur. On the other hand, if a single color appears in multiple disjoint regions, the grid is invalid because no single subrectangle can encompass all occurrences of the color. Another edge case involves empty cells, which must remain empty until explicitly painted by a valid subrectangle operation. Lastly, overlapping rectangles require careful handling to ensure that no lower priority rectangle overwrites a higher priority color. These considerations ensure the algorithm handles all scenarios robustly. Here, we start by importing the necessary module, defaultDict, from Python's collections library. This helps us manage the boundaries for each distinct color in the grid. Then, we define a class solution and its method is printable, which takes target grid as input. The grid represents the canvas we need to analyze. First, we determine the dimensions of the grid, storing the number of rows and columns in rows and cols. Next, we use a defaultDict to record the boundaries for each color. Each color's boundaries are initialized as float, inf, float, inf, float, inf, float, inf, representing the topmost, bottommost, leftmost, and rightmost points respectively. We then iterate through the entire grid using two nested loops. For every cell, we retrieve its color and update its boundaries. For instance, the top boundary is updated to be the minimum row index where this color appears, and the bottom boundary becomes the maximum row index. Similarly, the left and right boundaries are calculated based on the column indices. This step essentially maps out the rectangular area occupied by each color in the grid. After that, we define a helper function, can_print, to determine whether a specific color can be printed. It retrieves the boundaries for the color and iterates over all cells within that rectangle. If any cell contains a non-zero value that isn't the same color, printing is not possible. Otherwise, it returns true, indicating that the rectangle can be cleared. Once we have the can_print function, we proceed to the main logic of the algorithm. We use a set called printed to keep track of the colors that have already been successfully printed. While the number of printed colors is less than the total number of colors in color_bounds, we aim to make progress by clearing additional rectangles. We use a flag, progress, to track whether any rectangles were successfully printed in the current iteration. For each color, if it hasn't been printed yet and can_print returns true, we retrieve its boundaries and iterate through all the cells in that rectangle. Each of these cells is set to 0, marking the rectangle as cleared. The color is then added to the printed set, and progress is set to true. If, after checking all colors, no progress is made, it means there is either a circular dependency or an unprintable situation, and we return false. However, if we manage to clear all rectangles, the function concludes by returning true, indicating that the grid can indeed be printed according to the problem's constraints. Here, we begin by defining the main structure of our solution. The method isPrintable takes a 2D array, target grid, representing the grid that needs to be printed. We first determine the number of rows and columns in the grid. Then, we create a hash map called colorBounds to store the top, bottom, left, and right boundaries for each color present in the grid. The boundaries will help us identify the rectangular area where a specific color must be printed. Next, we initialize these boundaries by iterating through every cell in the grid. For each color, we update its boundaries, the topmost row, bottommost row, leftmost column, and rightmost column where the color appears. This ensures that we capture the smallest rectangle that fully encloses the color. Finally, we prepare a hash set called printed to keep track of the colors that have already been printed on the grid. To determine if a color can be printed, we define a helper method called canPrint. This method retrieves the boundaries of the given color from the colorBounds map. It then checks all the cells within the corresponding rectangle. If any cell contains a value other than 0 or the current color, it means the area is obstructed, and the color cannot be printed yet. If all cells within the rectangle satisfy the condition, the method returns true. Next, we attempt to print all the colors by iterating through the colorBounds keys. For each color, if it hasn't been printed and it meets the conditions in canPrint, we proceed to mark its rectangle as printed. Within the loop, we update all the cells in the rectangle to 0, effectively marking them as cleared. As each color is successfully printed, we add it to the printed set and mark progress as true. If no progress is made during an iteration, it indicates that the current configuration of the grid is either cyclic or unprintable, so we return false to signal failure. However, if we manage to print all the colors, the loop completes, and we return true, confirming that the grid can indeed be printed. This implementation ensures that we systematically check and print each color while avoiding conflicts caused by overlapping rectangles. The use of the printed set and the progress flag allows us to handle dependencies between colors effectively, guaranteeing that the process terminates correctly regardless of the input configuration. Here, we begin by examining a simple grid where the goal is to determine if the grid can be printed by a strange printer. The input is a 3x3 grid with two colors, 1 and 2. First, we initialize the dimensions of the grid, 3 rows and 3 columns, and set up an empty dictionary color_bounds to track the boundaries of each color's rectangle. Next, we record these boundaries by iterating through the grid. The entire grid is filled with color 1, except for the center cell, which is color 2. For color 1, the boundaries are the entire grid, top at row 0, bottom at row 2, left at column 0, and right at column 2. For color 2, which is confined to the center cell, the boundaries are top at row 1, bottom at row 1, left at column 1, and right at column 1. These boundaries are crucial for determining the order in which the printer prints the colors. With the boundaries recorded, we now proceed to check the printing order using a topological sorting approach. Starting with color 1, we observe that its rectangle spans the entire grid and contains color 2 in the center. This means color 1 cannot be printed yet because its rectangle is not homogeneous. Next, we check color 2. Its rectangle is a 1x1 cell that contains only color 2, making it printable. We update the grid by setting the center cell to 0, indicating that color 2 has been printed. The updated grid now reflects this change. Returning to color 1, we check again. With the center cleared, the rectangle now contains only color 1, making it printable. We proceed to set all cells in its rectangle to 0, completing the process. The final grid is completely cleared, and both colors have been successfully printed. Therefore, the output for this example is true. In the next example, we analyze a grid where printing is not possible. The input is a 3x3 grid with colors 1 and 2 alternating in a checkerboard pattern. Similar to before, we initialize the grid dimensions and create an empty dictionary for color_bounds. As we record the boundaries, we find that color 1 spans the entire grid, top at row 0, bottom at row 2, left at column 0, and right at column 2. Color 2, which appears in a vertical column, has boundaries top at row 0, bottom at row 2, left at column 1, and right at column 1. These boundaries are stored in the color_bounds dictionary. Now, when we attempt topological sorting, we start with color 1. Its rectangle spans the entire grid but contains color 2, making it unprintable. For color 2, its rectangle spans a vertical column but contains color 1, also making it unprintable. Since neither color can be printed, we detect a cycle, meaning no progress can be made. This indicates that the grid cannot be cleared, and the output is false. In this scenario, the strange printer fails to clear the grid because of the interdependence between the two colors. With no valid order to print the colors, we conclude that the grid is unprintable. Thus, the output for this example is false. Now, we consider a larger grid with 4 colors, 3, 4, 1, and 2. The input is a 4x4 grid, and as always, we start by initializing the grid dimensions and setting up an empty color_bounds dictionary. As we record the boundaries, we find that color 3 spans the left side of the grid, with top at row 0, bottom at row 3, left at column 0, and right at column 1. Color 4 spans the right side of the grid, with top at row 0, bottom at row 3, left at column 2, and right at column 3. Color 1 forms a rectangle in the middle of the grid, with top at row 1, bottom at row 2, left at column 1, and right at column 2. Finally, color 2 is confined to a single cell, with top, bottom, left, and right all at row 2, column 2. These boundaries are stored in the color_bounds dictionary, giving us a complete picture of the grid structure. With these boundaries, we move to the topological sorting phase. In the topological sorting phase, we begin by checking if color 2 can be printed. Its rectangle is a 1x1 cell that contains only color 2, so it can be printed immediately. We update the grid by setting this cell to 0. Next, we check color 1. With the cell for color 2 cleared, the rectangle for color 1 now contains only color 1, making it printable. We update the grid by clearing this rectangle. Finally, we examine colors 3 and 4. With the inner rectangles cleared, both of these colors now have homogeneous rectangles, allowing them to be printed in order. The grid is successfully cleared, and all colors are printed. Therefore, the output for this example is true. The time complexity of this solution is determined by analyzing the different steps involved in processing the grid. First, we calculate that the overall time complexity is O, R*C, *K, where R and C represent the number of rows and columns in the grid, and K is the number of unique colors. To break this down further, the first step involves recording the boundaries of each color in the grid. Here, we use nested loops to iterate over all our *C cells, identifying the top, bottom, left, and right boundaries for each color and storing them in a dictionary. This step alone has a time complexity of O, R*C. Next, we have the can_print function, which checks whether a color can be printed. For each unprinted color, this function iterates over the rectangular region defined by its boundaries. In the worst-case scenario, this rectangle could cover the entire grid, requiring O, R*C, operations. Since we call this function for each of the K colors, the total complexity for this step becomes O, R*C, *K. These two steps are key contributors to the overall time complexity. The next step to discuss is the topological sorting process, which is the main while loop. The outer loop ensures that each color is processed at most once, but in the worst case, we may need to iterate over all K colors multiple times until every color is successfully printed. The computational cost here is dominated by the repeated calls to the can_print function. Since we've already established that each call to can_print has a time complexity of O, R*C, and it's invoked for K colors, we see how this step also contributes to the overall complexity of O, R*C, *K. When we combine all the steps together, the dominant term remains O, R*C, *K, as the repeated calls to can_print across all colors outweigh the computational costs of other parts of the algorithm. Moving on to space complexity, we start with the memory usage for the color boundaries dictionary. This dictionary stores the boundaries for each of the K colors, with 4 integers per color, resulting in a space complexity of O, K. Another important component of the space complexity is the printed set, which keeps track of the colors that have already been successfully printed. Since this set grows as we process each of the K colors, its space complexity is O, K. For the target grid, the algorithm modifies the input grid in place, meaning no additional space is allocated for creating a copy of the grid. This keeps the space usage proportional to the size of the grid, or O, R*(C). When we combine these components, the total space complexity becomes O, R*(C plus K. This accounts for the size of the input grid and the memory needed to store information for each unique color. The efficient use of in-place modifications in minimal auxiliary data structures ensures that the space requirements are kept low, even as the size of the grid or the number of colors increases. When comparing this approach to a naive brute force method, the efficiency becomes clear. A brute force solution would involve trying all possible permutations of the printing order for the K colors, leading to a prohibitive time complexity of O, K. This is infeasible for large values of K. In contrast, our approach leverages topological sorting and boundary constraints, which reduce the complexity to O, R*(C, *K. Considering best, average, and worst-case scenarios, the best case occurs when all colors can be printed in a single pass, resulting in a time complexity of O, R*(C. However, in the average or worst-case scenarios, the algorithm may need to iterate over all K colors multiple times, leading to the worst-case complexity of O, R*(C, *K. The mathematical justification for this efficiency lies in the dominant term, which comes from the nested iteration over grid cells during boundary checks and the can_print function. For each color, the maximum cost is proportional to R*(C, and this process is repeated for up to K colors, making the overall complexity significantly better than the factorial growth of the brute force approach. When working on this problem, there are several common mistakes to watch out for. First, many solutions overlook the printing order constraint. Remember, the order in which colors are printed matters. If you don't ensure that earlier colors are fully printed before moving on to later ones, your solution may fail to produce valid outputs or correctly verify subrectangles. Another frequent error is misidentifying valid subrectangles. It's not enough for a rectangle to simply contain the color, it must be continuous and cover all instances of that color. Missing this detail can lead to incorrect validation. Additionally, brute force approaches are prone to being overcomplicated. While iterating through all possible rectangles is necessary, adding unnecessary nested loops or redundant checks can inflate complexity, leading to timeouts on larger grids. Finally, edge cases are often overlooked. For example, grids with only one color, grids where all cells share the same color, or cases where no valid solution exists need to be tested carefully to avoid unexpected failures. Now, addressing inefficiencies is another key part of solving this problem effectively. Inefficient boundary checks are a common source of redundant computations. For instance, repeatedly calculating boundaries for each rectangle during validation can significantly slow down the solution. Instead, you can pre-compute boundary positions for each color, which not only optimizes these checks but also simplifies the overall logic. From an interview perspective, there are several important takeaways here. One key insight is the value of pre-computing boundaries for grid-based problems. This optimization can drastically reduce the complexity of validating rectangles. Additionally, many grid problems can be tackled through a mix of simulation and pre-computation, so mastering the balance between these two techniques is crucial. It's also important to communicate your thought process clearly during an interview. Be explicit about how you validate constraints like the printing order and show awareness of edge cases. Finally, when optimizing your solution, it's often best to start with a brute force approach and then refine it incrementally by identifying and removing redundant computations. Now, it's helpful to examine related problems that can provide insights for Strange Printer 2. For example, LeetCode 85, Maximal Rectangle, involves identifying rectangles and performing boundary checks in a grid, making it quite similar in structure to this problem. LeetCode 221, Maximal Square, focuses on finding squares in a binary matrix but uses dynamic programming techniques that can also be applied here. LeetCode 200, Number of Islands, is another grid-based problem but emphasizes identifying connected components, which can be useful for understanding subrectangle formation. Lastly, while not directly grid-based, LeetCode 1286, Iterator for Combination, emphasizes systematic iteration and constraint validation. The skills required for that problem can enhance your approach to solving Strange Printer 2, especially when iterating through possible configurations systematically. Finally, let's explore some alternative approaches to solving this problem. One option is an optimized brute force method with pre-computed boundaries. Here, you reduce redundant boundary computations by pre-processing the grid, which speeds up later validation steps. However, this does come at the cost of additional pre-processing time. Another approach is a greedy method, where you attempt to print the grid row by row or column by column while respecting constraints. While this can be faster than brute force in some cases, it may fail for edge cases where the constraints are more complex. Lastly, you might consider a dynamic programming approach if applicable. With DP, you can track the state of the grid and determine valid rectangles dynamically. However, this approach typically involves higher space usage and requires careful design of state transitions. Each of these methods has its trade-offs, so the best choice depends on the specific requirements of the problem and the constraints imposed by the grid. Thank you for joining me on this problem-solving journey. We reviewed the Strange Printer 2 problem, broke it down into manageable steps, and highlighted key insights. Remember to keep practicing and exploring different approaches to strengthen your coding skills. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!